I work at Microsoft Research, also in the machine learning group. And I'll talk about machine learning. So just as a show of hands, how many of you have used or studied machine learning algorithms before? OK. Good. That's good. So hopefully the few of you who haven't will enjoy a lot of stuff, and then the rest of you will get a refresher. So just a quick introduction to what machine learning is about. So one way to think about it is that it's the general problem of taking observations of some sort and producing predictions for them, where the key constraint is that predictions aim to minimize some well-defined notion of an error. And we'll formalize this shortly and then give some examples. So formally, we have some domain of inputs, let's call it X, where each one of them is an observation that typically consists of some features. The simplest example is just a vector in RD. But you can think of observations having various string properties or categorical properties. And the goal is to create a function f, which will, given an item from X, will produce a prediction from some other domain Y, where the goal is to predict something of interest, which can be a label, whether an email is a spam or not a spam, or a quantity, such as the probability of a click on an item, or a structure, such as the parse tree of a sentence in natural language. So the loss function is really central to all of this, and that's what defines what we consider a good prediction. So the loss function will take the prediction that we produce, the value of f, and compare it to some true value y that is supposed to be there for the given x, which was not seen. And here we just give a couple of very basic examples. So for binary classification, we can think of notion of 0-1 loss, where we just predict a label, which is binary, and then if we guess it correctly, we get loss of 0. If we guess incorrectly, we have a fixed loss of 1. That's very intuitive because we just count the errors, basically, but it's numerically very difficult, as we'll see in the next slide. A slight modification to this is that suppose now we're predicting a real valued quantity with f of x. We're comparing it to y, and we'll penalize the difference. That's also very intuitive, but the absolute value is numerically unpleasant in several ways. So the third example, squared loss, is actually the most common example that's used in many practical algorithms, many reductions of algorithms. And here, what we'll try to do is we'll penalize the predictions which deviate further out from the true value of y harsher because of the square. This also will be differentiable. It's convex. So squared loss has a number of these very nice properties which make it very, very popular. And finally, the question is, well, that's all nice, but how do we actually find those prediction functions? And so that's where we first decide that we'll have a prediction function of a certain form. So we'll either have a set of weights for each feature, and then we can think of a linear predictor. Or, for example, we can say that, well, we'll be making rules with a certain number of split points or decision trees, let's call them. And we'll maybe combine up to 1,000 such rules. So in each of these cases, the notion of the function class will be just the space from which we're trying to find the one predictor that will give us the low error. And so a standard setting is where we have a training set of some known observations with corresponding perfect answers that we're supposed to get from it. And based on this training set, we will typically train our predictor by doing two things. First of all, we'll minimize the error of the prediction in the training set, because it should do well on the things we know have the right label. But also, there's this notion of regularization or overfitting that is central throughout many, many algorithms. And the idea here is that the simplest thing we could do is we could just memorize all the answers. We could just have a predictor which is just literally memorizes every x and the corresponding y. However, it would not do well on any x it has not seen. So this kind of gives you an idea that what you want is you want something that generalizes. And so to generalize, you have to prevent it from just fitting the training data as well as possible. And typically, this is achieved by having this separate term, which will penalize functions that have either very high complexity because they overfit, or have other undesirable properties, such as they have very high coefficients and so on. In different models, it'll be different. So a short discourse on the loss functions. So this just kind of gives you a geometric interpretation of what different losses correspond to. So here on the x-axis, we have this for binary classification. So our y is either +1 or -1. And f of x is what our predictor is producing for it. And to guess correctly, we want to be in the positive side. So if the label is 1, we want f of x to produce something positive. If it's negative, we want to produce something negative, so the product will be positive. So the black line corresponds to 0, 1 loss, which says that as long as we predict positive for a positive example, we suffer no loss. And then we have the step function to suffering the loss of 1. And this is, geometrically it's clear why this is bad to deal with in terms of differentiability and so on. And then there's many variants where we'll try to smooth this. I mean, first of all, there is this hinge loss, the green line, which says that, well, actually, what we don't want to do is we don't want to give us to suffer really loss no matter how confident we are. So we want to have 0 loss all the way out in the positive, but we want to scale it linearly with how wrong we are. So it's kind of a combination of 0, 1, and the absolute valued loss. And that's also very popular in a number of algorithms. And finally, there are these much nicer functions, such as the logistic loss or the exponential loss, which will penalize bad predictions more harshly and will result in very different algorithms and different sensitivity to outliers, for example. But one key thing to take away is that it's very important to realize when you're using an algorithm, what is the loss that is being optimized? Because that will determine how sensitive it is to different types of bad data or noisy features and so on. Just 2 examples to kind of ground everything. So one, let's take email spam. Our observations here for each message, we know what the headers are, we know what the body is, so we can create features corresponding to every word that we see in the message. We also have statistics on the server typically about whether this email, whether the sender sends out lots of messages to lots of addressees, or whether the recipient receives a lot of spam. And these give us also hints about whether a message is spam or not. Label, we just need to assign it a binary label of spam or not. And one important thing to talk about here is that the loss here is actually not as straightforward as the previous examples, because the 2 types of error have different costs. People get very upset when they get good messages placed in the junk folder. However, people are mildly annoyed but not terrified by some spam making it through into their inbox. So designing a loss function here would have to take into account this asymmetry of 2 types of error depending on whether it's a false positive or false negative. And that's a fairly common property for lots of prediction domains. Another example is click prediction. So if you're working in Yandex or Microsoft or Google or any of these companies, there's lots of applications where you're basically showing items to users in some context, and to select which item to show, you want to predict the probability with which the user will click, because we assume that click is a good thing and we want that to be high. So here, the observations that we have are various attributes of each of these facets of context, so query in search case, or say page if they're just looking at the web page. Item, if it's ads that we're trying to serve, it'll have some properties such as what's the text, how well it corresponds to the context, and so on. And finally, for users, we'll have some notion of where they are, what they have done in the past. So for each of these, we'll create different features where, again, our x will be just a vector of numbers that capture various properties of each of these facets. Our label is just in the 0, 1 interval, and the loss function typically used here is log loss, which has a number of nice information theoretic properties. But basically, we will be penalizing ourselves pretty harshly if we're very confident. So if it's a non-click and we're very close to 1, that's bad. And then, or it's a click and we're very close to 0, it's bad. And the convexity actually is a very nice thing that will allow a lot of algorithms to work well here. And at the same time, it'll be very intuitive in terms of what constitutes a good probability prediction for click prediction in online services. OK, so a quick introduction into several key types of learners. So linear predictors are most well known and most common. Logistic regression, linear SVMs, perceptrons are all examples of one-layer nets. Things you may have heard. I mean, they're all really the same class of predictor. The function is just a hyperplane that divides the space and corresponds to predicting positives and negatives in the binary case. And the function is really just a set of features weights on each feature. So it's very intuitive to say that, well, I'm thinking this attribute has this importance, this attribute has that importance, and so on. The second most practically commonly used class of functions, and also very nice intuitively, is tree ensembles. We'll talk about them a little more. Boosting and random forests are the 2 kind of brand names that are most popular in this area. And here, each function is just a set of rules, so you can think of them as splits on features. So we'll ask questions like, is this feature greater than some threshold or not? And depending on that, we'll go down the tree and make a prediction. The third class is what we call nonlinear parametric predictors. So neural nets with more than one layer. Bayes nets are examples of these models. So here, the model is described by a set of parameters, which is trained during training. And they are able, the key differential here is that they're able to produce arbitrarily, or they're known as universal predictors, so arbitrarily shaped decision functions. The cost, of course, is that they are more difficult to train. And finally, there's a notion of nonparametric predictors. K-nearest neighbor, kernel-less VMs, Gaussian processes are most prominent examples. And the way to think of this class is we're just taking a set of examples. From all the examples we've seen, we're retaining some small subset and thinking of them as anchors or sort of as the important points with some importance weight. And then for new points, we'll just look at the ones that are closest or we'll weigh their contribution by their distance in some space. But the key thing here is that we're not just learning parameters, we're actually retaining a subset of the training set, and that makes it different. How do we actually train those things? So for each of the classes, there's dozens and hundreds of algorithms. Given the time constraints, we'll just talk about two core patterns that are present pretty much through all of them. So one very common pattern is that we typically want to arrive at a good predictor f by starting with some predictor and then just doing stepwise search. And of course, if you're doing stepwise search and if you have a loss that you're trying to optimize, gradient descent is naturally the first thing that comes to mind. And there's lots and lots of variants of it. So stochastic gradient descent is probably really popular right now. The idea is that you'll do updates very quickly for each example you see, literally. There's other variants, so coordinate subgradient, where you will update only subsets of features. And then extensions of this will include not just taking into account the first order curvature, but also taking into account the second order. And actually, the interesting thing is that the notion of just arriving at a better loss value by stepping in the function space actually underlies other algorithms like boosting, like trees, except that it's a sort of a mind trick because you're not tuning weights, really. You're actually adding more trees. So the way to think of it as gradient descent is that if you think of the space of all possible trees you could have, how do you move through the space? Well, you add another tree, and then in the end you'll average their predictions. But effectively, this corresponds to a form of gradient descent in function space. And there's been algorithms that have derived just from this view. And finally, another example that's kind of very different, but for nonparametric models, when we're training SVMs, for example, typically what you do is of all the training examples, you want to select some subset that you will retain as your support vectors. Again, you will iteratively update those weights on the support vectors that you keep in mind. So the overall pattern of the algorithm just iteratively converging on a better predictor by reducing error stands for those classes as well. And the other very common idea throughout a lot of training algorithms is that, well, we know how to train a single predictor, but very often it really pays off to have multiple predictors that we will then aggregate. And the first intuition is that, well, you just, by training each predictor, you have some variance because the training set was just a sample. So to reduce this variance, you're doing this in multiple subsets, and then by averaging them or averaging their outputs or having sort of combiner, you're reducing this variance and arriving at a more stable reduction in the loss value. So Bayesian random forests are examples of these types of models. And another type is that what you can think of doing is also, say, training a linear model on each subset, and then instead of averaging their predictions, you can average the actual parameters, arriving at just a single linear model. This is known as parameter mixtures. But generally, it's the same idea of just of aggregating multiple predictors. Okay, so since this is all about big and large and so on, just kind of a, and actually, do people have questions? I'll pause. This is a good place to pause. No? Okay. So large data sets are great, and they give us much better predictors, and they're very useful. However, one key thing to keep in mind is that in machine learning, it pays off to go bigger and larger, only if bigger and larger actually gets you better predictions. And surprisingly often, it's not the case. And the bottleneck happens because a lot of the time, if you select a fairly simple function class, let's say a linear model with not too many weights, There's plenty of results which show that actually you converge on optimal weights for a given loss in a number of examples that is linear or sublinear, which means that having terabytes, petabytes, and so on actually is not really buying you anything other than, I don't know, more grants money or something. But so keeping in mind that really it's important to control the accuracy improvement when you're working with large data is key. But there's also other sides to scaling up that are not just about more data being pumped into the trainer. So large models is a very interesting set of problems where you can think of several subsets. We'll go into one of them. One is, what if you have many, many features? And by many, we mean billions and beyond billions. So if you think of text, well, there's millions maybe of words at best. But once you're starting taking into account sequences of words, you can arrive at billions fairly fast. Also, once you start looking at combinations of features, you can get into billions. And here, the data sets may not be very large. I mean, they'll fit into your cell phone. But the models actually are fairly large. And that's a very interesting class of problems around scaling up. Ensembles is another interesting problem where scaling is a different dimension than just data size. Because here, think about those trees and combining many trees. Typically, you do keep improving as you grow them. And it's a hard problem of how to actually do this effectively on multiple machines, multiple cores, and so on. And then there's kind of a more recent popular example is so-called deep networks, where the representation within the network is grown by having more hidden layers, which allows you, on one hand, to model more dependencies in the features, but also the bottleneck is not in the data throughput, but really in the computational throughput, which is why GPUs, for example, are used. Model selection is another interesting class of scaling up problem that's not data bottlenecked. And here, the dirty secret of machine learning is that all of these wonderful algorithms, they all have some hyperparameters. Typically, it'll be some constant, or it'll be several settings, or it'll be a choice of a, say, data normalizer. And the way everybody does this is pretty much by trial. You just sit there and kind of turn things until the numbers get better, which is pretty sad, but is really the way that kind of the state of the industry right now. And here, doing this well requires doing lots and lots of trials of the same learning algorithm, but with different settings, sometimes on the same data set, sometimes on some samples. And this has its own problems related to scale, because now you're scaling with runs on the same data set on different nodes, but you want to interact and inform each other. And finally, we talked about learning here, but this inference is just a keyword for prediction. In some problems where the output is structured, so speech recognition, for example, you're not predicting a single, I mean, at the level of phoneme, for example, or word, you may be predicting a single thing, but ultimately you want to predict entire sequences. And this becomes hard as soon as you try to take into account that some sequences make sense and some sequences don't make sense, even if individual words seem just right phonetically. And this means that once you train a predictor, it's not like you're done, because actually running the predictor on the input is a hard part, even after you've learned it offline. And there's a whole set of nice problems around that. So the point is that the challenges presented by these different settings are fundamentally different, because depending on whether you're doing inference or learning, are you really fighting the fact that you have too much data, or the fact that your model is very large, makes your bottlenecks different, makes your data flow different. And so that's why, when people talk about scaling up learning, there's not really like a single solution that, you take a certain model of GPU and then use a certain type of algorithm, and there you're set. I mean, it's really becomes domain specific. So this is kind of the rest of the talk is just a sample of several things from all of these very interesting areas. So let's look into one class of models, just the linear models, and just consider how do we actually scale them to run on big data. And so SGD, or stochastic gradient descent, is the simplest, nicest, easiest to implement. Learning anyone can implement it literally in 5 minutes, because all you're doing is you just have a set of weights for all the features you have. Let's call them W. And you're just going to run through your training data set, take your current weights, look at the output that they produce, and then if the output is bad, or basically you look at the you look at the loss, and then you'll just do an update with a simple gradient step. So here we just go until we're done, and at every step we'll take the previous weights and take one gradient step with some step size alpha based on the loss gradient at current points, at current point xt. So for example, if we're using this hinge loss where we suffer 0 loss, no penalty once we're confidently predicting the right thing, or we're suffering linear penalty if we're not predicting the right thing with a certain margin, the update will just become a simple addition of the example's features to the current weights, scaled by, of course, scaled by the sign of the label. But also there's this alpha is the current state of the art is that people typically will use this 1 over square root t damping factor for the algorithm to converge. And that really is all the algorithm. So you're just going through a training set linearly, updating the weights on every example. Once you stop making errors, you will not make any updates. Your updates will become smaller and smaller as you keep going, so it converges nicely. There's lots and lots of work in optimization theory and theoretical machine learning on sort of the better ways to have the weight constant. But the bad thing about this is that because we're doing these updates one by one, it doesn't allow us to parallelize it on data cleanly. Because fundamentally, every example we see, we're going to change the model immediately if we make an error. So we cannot, in parallel, sort of do something to another example because the other example will be using stale weights if it does. So people have proposed various tricks around that to parallelize this. So the obvious one is, the first one is just a mini batch. So instead of an update on every example, you'll do an update on the gradient accumulated on, say, 10 examples, and each example will be processed separately. And then there's also been more interesting recent work on, well, what if we just have multiple cores, they all update the weights independently, and we actually don't care about synchronicity, and shockingly, it actually works well. But the point is that actually, do we really care? Because once you implement this well, this will literally run, if you're talking about big data, and linear models are typically useful when you have big data, this algorithm actually runs at I/O speed. So this is not a really good laptop, but it can go through a gig of a well-known text data set in 12 seconds. There's also fairly few parameters. So, and you're doing linear learning. So that's why here, would you be more concerned about speeding up the core algorithm or trying to go nonlinear, for example, and actually, if you have more data, and learn patterns by not doing the updates in parallel, but by having a more complex model instead. So one step in that direction, let's consider a different, slightly different setting of the same problem. We'll also have a linear learner, except that here we'll have a specific type of loss function known as logistic loss. So logistic loss is the one that will penalize will penalize worse as we're making worse errors, but will do it not as dramatically as, say, squared loss. Logistic regression or maximum entropy classifier is the sort of brand name for this type of model. We're trying to get the good W weights, and we'll typically penalize too large or too small values because that corresponds to feature selection or sort of regularization concept that was introduced earlier. So one way, so in the previous slide we talked about SGD, where we're just running through data, doing an update of the loss function at every step, and that's with a fixed rate. One thing that doesn't take into account is that it doesn't take into account the actual curvature of the loss surface. And the way to do this would be to use Mutant methods. The problem is that sometimes we can use Mutant methods, sometimes we can't because we don't have the second derivative, or if the second derivative is just very expensive to approximate. So here, if we're talking, say, about text classification with words and pairs of words and so on, we're in the billions of parameters territory. So computing the Hessian matrix becomes pretty unpleasant. So we don't want to do that. So instead, there is this class of algorithms which is sort of a next step beyond SGD that will try to do second order methods without explicitly computing the Hessian. So we'll just do the same gradient step, except that we'll scale the gradient update by the inverse of this pseudo Hessian, which will be estimated from just the recent history of weights and gradients. And the limited memory trick refers to the fact that we're just approximating the Hessian indirectly. This parallelizes very nicely because unlike the previous algorithm where we updated for every example, here we'll go through the whole batch of examples, accumulate the update gradient, and then do a single step. So here we can easily do this in parallel for different subsets of the entire data set. However, if we try to use different platforms, like say, take MapReduce, for example, it will not work as nicely because here what happens is algorithm progresses is we need to drag around the weights, we need to drag around the history of weights, we need to, once we aggregate the updates from all the examples and compute the overall one, scatter it back to all the worker nodes. And typically in commercial MapReduce systems, the types of communication that are needed here, which is this all reduce propagation back to all the workers, having stateful workers, is just not supported. So in response, people have found variants of algorithms which are not as simplistic as SGD, but which will leverage basically the strengths of MapReduce, which is going through tons of data in lots and lots of workers at the same time, but also not require a lot of the communication or not require as much iterations as vanilla LBFGS. Okay, so let's talk about trees. Trees are great. Trees are very intuitive. So a lot of the decision making that humans do on a day-to-day basis will either, I mean, it's an open question whether fundamentally each of us is just a neural net and it's not really a tree, but at least when we talk about things and when we vocalize it, we will typically express most of our predictions as rules. So if you want to predict whether your students will show up to class and they're into skiing and bicycling, you can make a simple decision tree that will tell you that they're not going to come if they're skiing or biking. So if it's not raining and if it's not too hot, they'll go biking, or if it's snowing, they'll go skiing. So basically, we'll express this rule as a tree where at each node we have a feature on which we're making a decision, and then we go either left or right. And then at the leaves, we arrive at the prediction. So the nice thing you can see is that here, for every prediction, you don't need to care about all the features. Like with all rules, you're just selecting a few key features, and their combination corresponds to the prediction you're making. So this is very easy to understand, to express, to debug. It's also very easy to extend by saying that, well, we don't have to just predict a label. What we can do is we can predict a numeric quantity, so let's call it, and then we'll call it a regression tree. There's also variants where you can have a linear model, for example, on the leaf that'll take multiple features. And then we'll do multiple of these. So what we'll do is we'll say, make a first tree. It'll make some mistakes. What we'll do is we'll train another tree, which will try to fix the mistakes that the first tree makes. And then we'll keep going and going and going. So, and there's, of course, variants on this idea where, well, you may want to train these trees not sequentially, but in parallel on different data subsets. So there is lots and lots of different variants of tree algorithms that use different types of combiners between the different trees if multiple trees are learned. You can have different models for prediction in leaves, and you can have different types of split conditions. So either just split based on the value or have more complex conditions in there. And just a quick run through a number of examples. Boosty, Red, and Forest, like I said, are sort of the canonical families of algorithms, but even within them, there is a whole number of different algorithms that differ in the loss function used, in the way that the learning rates, say, updated, and so on and so on. And of course, there's very interesting modifications of this is once you talk about these structured tasks that are like tree prediction or ranking that are not just classification or regression, doing trees becomes tricky and even more interesting. So trees are hugely popular. They're arguably the first thing that anybody should ever try on anything if they just want to try something. They're a little trickier to code up than, say, the SGD, but if you have a good package, they should be the kind of standard screwdriver you always try to plug. First of all, because they work very well. There's a number of domains where they are state-of-the-art. I mean, in Vision, things change year to year, but currently trees and random forests are the favorite tool of Vision people. In web, trees, like for search ranking and so on, trees are very, very popular. Biologists like trees because they're easy to understand. They're also pretty efficient because you're at prediction time, you don't have to look at all the features. You're just going through a small subset of splits and arriving at the labels. So that makes it straightforward to use, and you can also optimize the process pretty well. And they've been studied for years and years because at some way you can think of them is each one of them just makes a single coordinate split, so you're just learning half spaces. The kind of favorite term in the learning theory circles is learning half spaces, and there's been lots of great work theoretically. And they have a lot of properties that in practice make them very usable. For one thing, that a lot of time your data is not just perfect numeric vectors. It'll have features that are discrete. It'll have features that are missing. And we're making splits. You don't care about how, how does a question mark doesn't fit into Euclidean space, right? But you can make a split that just says that is the feature missing or not. So that makes them very usable with diverse data you typically see in practical applications. Feature selection is effectively an algorithm. If the feature is useless, you just won't split on it. So you don't have to worry as much about feature selection as with linear or nonlinear numeric algorithms. Sweeping is fairly well understood. So the number of leaves, for example, the learning rate for boosting, and the parameters, they're reasonably well behaved. And also they scale, somewhat surprisingly, because trees were popular in the 90s, then not popular in literature for a while, and then sort of recently came back. And it turns out that scaling them was thought to be hard, but it's actually not. It requires some work. But let's talk about it for a second. So so first let's talk about tree ensembles. So there's two fundamental types of tree ensembles. So tree ensembles is when we learn a tree, and then instead of one, we'll learn a whole bunch, and then we'll combine their predictions at prediction time. So one simple variant is known as bagging, where what we're doing is we're going to give each tree a different subset of data. So bootstrap is known where it's basically sampling with replacement. So if you think of the data here as I don't have a pointer, unfortunately. So if you think of the original data matrix, I don't have a pointer here either. But basically, you're resampling the rows for each training set. And then you're training each tree on some different subsample. So each tree in the ensemble ends up a little different. And in the end, you'll combine their predictions. And the idea is that you reduce variance this way. Random forest extends this idea by saying that, well, we're actually going to make them different, not just by giving them different training sets, but by also forcing them to be different at split points. So we will randomly select just a subset of features on which every tree will be considering a split. And as a result, they will come out quite different. And there's been work on showing that wide diverse ensembles are good, because basically they prevent you from overfitting and so on. So, but fundamentally, the core algorithm is the same. And the nice thing to remember here is that, well, each tree is just done on its own. So we can just embarrassingly parallelize it by just taking subsamples of the data and then training each one totally independently. And then in the end, we just combine all of them, we're done. We're not even combining, we're just kind of taking them and stacking them together for prediction. So boosting, which is the other fundamental family of tree ensemble algorithms, is different because here what we're doing is we're going to first train a tree on just our original data set. And then what we'll do is we'll look at the errors that the tree makes. And then the way to think about it is that we'll reweigh the data set for training the next tree in such a way that the tree will focus on the errors that the first tree made. And this is what corresponds to this notion of gradient descent in function space, because we're going to taking this by adding the second tree, we're taking a step towards a better ensemble, which will reduce the error by actually looking at the gradient. Boosting is, it's one of the algorithms where there's actually multiple. So there's the interpretation of functional gradient descent. There's the interpretation of combining a mixture of experts of weak learners. There's actually a really interesting game theoretical interpretation where you can think of the algorithm as playing a game versus weak learners, which is I urge you to spend any amount of time on studying it. But each of them gives a rise to a different, slightly different variant of the core update algorithm. So if we think about the descent in function space, because each subsequent tree will aim to take that step along the gradient, what we can do is actually, we can, instead of reweighting the examples, we'll actually change their labels a little bit. And the way to think of it is that, well, each tree is just is basically introducing some distribution of outputs over the examples. So we can alter the distribution by, instead of the original labels, plugging in the point-wise gradients of the loss with respect to the current model. And so this is actually numerically very simple, because for standard losses, this just corresponds to a very simple, basically just what's known as a residual in statistics, a very simple function of the true value and the prediction value. And now all we're doing is none of this reweighting stuff. We're just changing the labels for the next tree. The next tree will kind of see a different data set which corresponds to a reweighted one. So the problem is that when we're doing it in sequence. So each subsequent tree is learned after we've already trained the previous one, got the predictions with it, which is bad for parallelizing. So what we're stuck with here is that if we want to scale this up to lots and lots of inputs, we can't really parallelize the ensemble construction, but we can try to parallelize the actual tree construction at each node. And again, this will, of course, translate to the things like bagging and so on, but here we're sort of stuck with having to parallelize the tree itself as opposed to an ensemble. So if you think about the algorithm, the way the actual tree growing algorithm works, what we're doing is that at every step, we're just considering all the features that we have for the examples in the current leaf of the tree. We're considering a number of possible splits, and then for each split, we'll have a notion of utility or goodness or loss reduction of basically we pick the best one. So the key thing, the key efficiency that we can do here, can exploit, is that first of all, we can consider just a small set of split points. So instead of, say, along the numerical lines, considering is x greater than 2, 2.5, 3.5, and so on, we'll be smart about selecting which splits we'll consider, which means that for discrete features, for numerical features, we'll have discrete beans. And then for these discrete beans, we'll want to have those that actually will give us good properties in terms of minimizing the error. And then splits are just the bin boundaries. And then what we can also do, it turns out, is that we can compute the utility of every possible split over every possible attribute in just going a single run over the data set, which is not very surprising, but that's where we'll go into a little more detail. So basically, once you've split, so here we're just looking at one feature, like say temperature or the click probability for from past impressions. So we'll split it into those bins from the original numeric values. And now when we're considering splits, we're just considering the number of the possible boundaries that the bins introduced. And if we think about what the gain of every possible split is, it is actually linearly accumulated as you go through all the examples, because each example that you have falls into one of the bins. So all you care about fundamentally for every bin is how many examples are on the left and how many examples are on the right, and how much, what's the average output and the total output on the left and on the right. Because the value of splitting at the current bin will, after we split, we'll just predict the average for every half. So the fact that we're going to just predict the average means that we can, in a single pass, find out what's a good split. And so on the right, you can see this little matrix. So the key data structure that will be used throughout all the tree learning algorithms is this what's known as the feature bin histogram, where we're basically going to just record what is the split value for every possible bin for every possible feature. And of course, in algorithms that subsample, there we don't have to literally do it. We can think of this as a sparse sample from this big matrix if you have lots and lots of features, or if you've subsampled the features. So all we're doing then is we're just going to pass through all the data set, aggregate the statistics for each split, and then select the best one. The nice thing is that we can do this in parallel for multiple nodes at the same level. So if you think of the data set here, and we colored it after the first split, some part of it went left, depending on what the value of the corresponding feature of the first of the purple split is, and some went right, or sorry, up and down. So here we'll say, well, actually, what will happen is that you now for the blue and for the red parts of the data set, you'll have its own histogram, and each example's feature value corresponds to incrementing one of the cells in the histogram matrix. So the thing is that if we're now doing this at lower levels, you'd think that, well, one way to do it is to do a pass of the data and then update all those in A and B. But we can keep all of them in parallel and sort of do this at the same time. So here, when we're considering the splits, we're actually actively constructing the full histogram and then considering what is this full split for each of the sub-branches all in the same pass, which allows us to avoid multiple passes of the data set, which is nice because this way, if it's very large, you're reading off the disk, you want to keep reading off the disk just once. So basically, for the entire level, we'll just do a single pass of the data, update all the necessary histograms, and compute both splits just in a single pass of the data set. And then another thing that's not as obvious is that actually what we could do is we could either split the entire data set by instances on multiple workers, Or we could also split it by feature. So every machine could be responsible for just a subset of features. All it needs to know is which example go into which sub-branch. And so that gives rise to sort of two ways to parallelize the algorithm, by feature or by instance. Or actually, you can think of even hybridizing those two. But that will be a really nice way to solve it for either the cases where you have a lot of data with not a lot of features, or not a lot of data but a ton of features, and then correspondingly the pattern changes a little bit. I'm going to skip a lot of details on how this actually those two things work. I mentioned the slides I'll probably make available, and I'll jump to something different, which is fun. So this whole many features thing. So it used to be a time when tens of thousands of features were considered a lot, millions were a lot. Well, now you have to have billions at least, right? So billions actually is not that hard. So suppose you take a big corpus of English, and we just look at all the number of unique words, pairs of subsequent words, triples, and so on. And all it takes takes us to go to 5 words to arrive at billions of possible combinations. Interestingly, it actually stops growing, and if you can notice, it starts declining a little bit because there's obviously a lot of structure in the language, so it's not like we're just generating random words. Actually, the patterns become fairly stable. However, you still end up with quite a few, a lot more than would fit with just a single word model. So this is difficult. This is difficult because if you're thinking of just even learning a linear model on these guys, now we're talking about learning billions of weights, which obviously will have very high correlations. But more importantly, suppose you're training, like, say, a spam model. You want that spam model then to ship to, say, every server on like if you're running, Yandex Mail, Hotmail, whatever. You have many servers. You want every server to have this model. If the model changes a lot, you need to update the model. We're talking about, so now this becomes heavy. The server ideally will also have many models, one for spam, one for web serving, and so on. So actually, we don't want to have heavy models. Learning billions of features will be fairly unstable, so you'll have to regularize very aggressively. But in general, it's also just intuitively really bad because you're staring at these long arrays of weights. You never know does this mean this word is important or it's correlated with a whole bunch. So how do we compress? Just another motivating example. So if you thought billions actually is not that bad, again, you say, like, well, the cell phone memory fits it. Once you have a task like the click prediction, where you have multiple dimensions. So you have users, and you have hundreds of millions of users. You'll have ads or ad pages or web pages or queries. Okay, hundreds of millions, billions maybe. But to do well, you actually want to have these combination features. You'll want to have a feature of a combination of a query and page, and say the number of clicks that the pair has received in the past month. And there you immediately blow through the roof. And also, once you have lots and lots of examples, you basically you start having these very unique features for which you don't want to learn individual weights. So the problem is that also, if you're doing this in a domain where data changes a lot, like anything online, you'll want to retrain very often. But you don't want to do this to take long. You don't want to take this more than a couple hours. So this is where the memory becomes the big issue. And then also, you want this to be decomposable in the sense that you may want to have some set of features on one server, another set of features on a different server. So billions become very unpleasant here. So there's a very simple trick which works amazingly well. It has been discovered and rediscovered numerous times, actually. So the best trace I know is back to the '88 paper when folks who did neural nets. The current incarnation was discovered by people at Yahoo in '06. Feature hashing is sort of the current way it's named. But the idea is that, well, so, okay, if we have a very high dimensional space, we typically want to project to something lower dimensional. Great. There is a great number of algebraic methods to do this. Typically, you'll need at least O of D, more often D of O of dm storage to keep your projection matrix. You'll have a cost of doing the full vector matrix multiply for them. Typically, good luck updating your projection matrix once your domain changes. So that's sort of all unpleasant. So there is a very simple, different way of doing this, where what you can think of doing is that you have your initial huge multi-billion vector, but in reality, only a small subset of features actually are non-zero, right? So in every message, you just have the words that are in there that have non-zero weight. So what you can do is that you can take each one of them, take the index of the feature that's non-zero, and then map it through a hashing function, which means the mapping will be stable, to a smaller dimensional space, like say millions, tens of millions. And the really important trick here is that when you're doing that, of course, you may get collisions because you're going from billions to millions. The collisions are going to be actually really rare if you think about it, because in the case of every single vector, more often than not, you'll have just like say dozens or hundreds of these guys, and you're mapping to 10 million or so. But if you do, the important thing to make it unbiased is to actually not just map, but also to add this random multiplication by +1, -1 in front of every projection. And so this has the property, so nice mathematical property that in expectation, the kernels computed on the projected representation will actually be consistent with the value of kernels computed in the original data, which sort of makes anyone who works with SVMs feel happy about it. And this is also very simple, right? Because all you're doing, you're just literally computing a simple, you just have a hash function, so you don't need to worry about these giant matrices that you're dragging around. You just literally have a stable hash, and that's it. The problem, of course, is that this is completely random. So there's not really a way to mold this in a way to reduce collisions that matter. There's been some follow-up work, but it's not sort of very computationally pleasant. But if you have a problem where you have billions, this is, again, sort of a very dumb but effective thing to try. OK, and I'm almost out of time, so I'll just kind of summarize. So this was a lot of things in 45 minutes. And I apologize, but that was the problem setting. So if you were, so sadly, there's not really sort of a singular lesson or formula or trick to that at least that I know that I can teach you. If anything, that there's a lot of choices. There's choices in terms of the learning algorithms, and they will have different properties. But in relation to scaling up, the choice is typically a platform. And thankfully, we have lots of them now, from these sort of MapReduce type platforms to GPUs and so on. And unfortunately, again, there's no trick. It's just that you have to be very cognizant of what each platform's strengths are and weaknesses versus the patterns in the learners. Because typically, if you go to higher order platforms like MapReduce, where you have these very nice high-level operators for distributing computation, as soon as you go to implement algorithms that have fine-grained control and data flow, you will run into the boundaries of the platform. However, it's very simple to implement, so it's always, one constraint is always sort of the programmer time. At the same time, there is a variety of other ways to parallelize using multi-core GPUs, just using TCP for machines talk directly. One constraint that is there and that people, I think, in literature don't pay attention to is that there's immediately a huge penalty in terms of the complexity of debugging and implementation. So that should be kept in mind when you actually have a choice of what to use. And then also here, the successes become much more specific to the right pairing of the platform and the algorithm. So for example, GPUs are amazing for speeding up neural nets. They are, so far at least, we've spent a long time on this. Well, we'll spend some more, but we found them nearly useless for a number of other methods like LBFGS, compared to a well-designed, just in-core implementation that uses things like AVX and so on. And what it comes down to usually is that you usually will have a trade-off between the platform's properties, such as the contention and latency for all the resources, versus how fine-grained of an update structure the algorithm has. And you typically want to match. Basically, if your updates are very frequent, you'll want them to not be bottlenecked by the architecture constraints. If they can be aggregated, then you don't care. You can basically pay the penalty and just do it in parallel in a more greedy way. But be smart. And I'll take questions gladly. Now or after.
Are there any examples of scaling up
interior importance methods. There are, so in the context of SVM solvers, there have been work. As far as I recall, what they've done is they've combined MapReduce and multi-core. So it was a weird combination where they actually changed, like they kind of like start with the standard, but basically it was, so like personally I thought it was a proof of concept, but in terms of the implementation it seemed very, I'll be able to give you the reference, but it just seems very fragile. But it can be done. I think that, and they did use multiplexers because they had to sort of jump through very complex hoops around it. It was a group at Hewlett-Packard Labs in 2007 that did that. I'll give you the reference. Yeah. If you're shy, I'll be around.